So they're proud to go live on YouTube. Now I am, though. Okay, I guess while Pinbox works on that, I'm going to still work on this.
Okay.
So we're about to go live on YouTube.
Voice and video. Output device. Headphones. Let me try that. Oh, that might have worked.
Oh, testing.
Yeah, I got you. Okay,
hey.
Good. Hey, sorry about that.
No worries. How have you been?
Yeah, pretty good. How about you?
Pretty good. Still, my voice is still pretty crappy, but this is an improvement, so.
Oh yeah, you sound a little bit like something might be going on. So if we got a break early or something, feel free. I mean, you don't want to overdo
Okay.
it.
Yeah, we'll see how long it holds
Yeah.
up. I was like nearly mute for Thanksgiving, so
Oh man.
this is progress for me.
Yeah.
Were you able to get through chapter 9?
Yes. In fact, I read it all this morning. It was kind of a short
Nice.
chapter.
Yeah, it was.
And I felt like I understood most of it, except for that stuff on displacement current at the start.
Yeah, I don't feel very solid on that either.
Yeah, I remember reading about that before and not really understanding what it was, what it represented. Is it actually a current or is it something else?
Yeah, like I was trying.
It seemed like it had to do with the change in the electric field or something.
Yeah, so it only matters when the current is changing, as far as I know. I was hoping to be able to like say like, oh, these electrons have to do with the displacement current, and these ones have to do with the regular induction, but I don't think it's like that. It's not as far as I can tell. So I think it just represents like when the current is changing, but I'm still not like clear on physically what it is.
Yeah, that picture in the chapter where they showed the capacitor and the plates,
Mm-hmm.
and what were they saying? So they were saying that capacitor was, I forget if it was being charged or discharged, but as the current is sort of, as the electrons are moving around inside the plates, the electric field is changing, I remember.
Yeah.
And I think when the electric, so it's something to do with the time derivative of the electric field, right? That's where the
Mm-hmm.
displacement current comes from, or how it's defined anyway.
Right.
So
And so
I don't know.
I I'm trying to rationalize it. I guess you know the field is related to the actual charge contained in that solid with Gauss's law, so it feels like there's still some kind of like there feels like that there's something there with like being able to figure out which electrons have to do with it, but I'm not really quite sure.
Hmm.
Actually, I don't remember being that clear on if this was a line or a surface. I guess they use S, so it's probably a surface, and they're doing like a Gauss's law.
Yeah, I imagined it was like a doorknob shaped kind of surface,
Oh
right?
yeah, that's a good way to
Um,
describe it.
yeah. But then they broke it into S prime and S, and I didn't quite follow that either.
Yeah.
I know S prime was the curvy part, and S was just the sort of the circular end of it.
What do they talk about? 9.4.
9.4.
Or like it's in section 9.2, but it's figure 9.4.
Yeah, I didn't understand that. Oh, figure 9.4. Okay. The white arrows and the black arrows. Yeah. So I could see that the black arrows are following the electric field lines from figure 9.3 and kind of going in the opposite direction.
Um. Oh, Yeah, that's true, isn't it?
Yeah, if you like superimpose figure 9.3 on top of figure 9.4, those electric field lines would land on top of those little black arrows, and they're going in the opposite direction.
Okay, so
I
I
think so.
completely missed that caption, I think. So if this is a current, why it's just out in the air and not in a wire? That's weird.
Sorry, can you say that again?
So they're saying the displacement current is the black arrows, but those are just like outside of the circuit.
Yeah,
Like they're not
so
in a wire.
no, I know. So I have a feeling it's not really like a current as we would think of it.
Yeah,
I think they just call it a current. I don't really know why.
maybe it's like energy in some form or something.
Yeah.
Huh. Maybe if Cook happens to pop in, that's something we can ask him about.
Yeah. They did say something about it having a sort of a strange name, right? Like Maxwell gave it a name and what does it
Oh
say?
yeah.
Maxwell called it displacement current. The name has stuck, although it no longer seems very appropriate.
Hmm. Okay, well, at least we're equally confused there, I guess.
Yeah, I know it. So let's see. Why does it come in? It comes in because there's a time changing electric field, right?
Mm-hmm.
And so it's something to do with Ampere's law, I think. There's some kind of correction factor for
Yeah, it was for that
Ampere.
divergence of J thing, or what is it? Oh no, curl B is equal to mu naught J. That's where the contradiction happens. Hey Rex.
Okay.
But they do use Ampere's law somewhere in here.
Yeah, Ampere's law is, what does Ampere's law say? I've forgotten. Isn't
That's
it curl
the
B is mu naught J?
oh, that might be the differential version.
Yeah,
So that's something like the line integral, but yeah, that might be the same thing.
it might be. Yeah, again, this morning when I was reading this section, I was thinking, man, my vector calculus is letting me down. Because they were talking about divergence of the curl and everything, and then later in the chapter they used some kind of an identity. Remember when they were talking about relativity, and
Oh yeah,
they
yeah.
said, oh, the divergence of this is equal to the cross product of this and the cross product of this, and I thought, oh, I didn't know that was an identity.
Yeah, no, I
Uh,
definitely not solid enough on the vector calculus to understand all the like proof stuff here. Hey Joven.
yeah.
Okay, there's the integral Ampere's law. They should say the differential version somewhere. Oh yeah. Okay. Differential form of Ampere's law. Okay, yeah. Nice. Anything else about chapter 9?
Let me just look at the list of sections here. No, I mean, like I said, I thought maybe it was one of the most gentle seeming chapters that we've done. It seems really short, didn't it?
Yeah, it was like 20 something pages, I think.
Yeah, and if you look at the questions at the end, it only goes up to like 32 or something, the whole thing. So I think it's just a short chapter.
Yeah, I guess it's kind of tying together
nice.
pretty much everything before this.
Yeah.
Rex got a new laptop, doesn't work on USB plugin. Oh, that sucks. Joven, this is a reading group we've been doing on Saturdays for electricity and magnetism. We're really deep in this last chapter that we're going to do as like the group, but we're working Maxwell equations right now. We're about to do some problem solving. Hey Jed, hope your Thanksgiving was good. Gobble gobble. And hey Rapture. But all right, you ready to I guess get into some problems?
Yep. No time like the present.
Okay. I did post the Excalibur link in like the text chat for this voice chat.
Yeah, I saw you were in there. Let me see if I can get in there. Yep, let's see. I think I'm here.
Oh yeah, I see it.
Yeah.
Okay. So I get a small star on this one. I'm still not sure exactly like where to take it. This equation del cross B equals mu naught J. So hey, Arrow Engineer, this is Purcell and Warren.
I think it's a little bit of a step up from Surway.
Oh, okay.
I got a physics text by Surway. It's a nice book. It's a nice book.
Oh, nice. I haven't heard of them. Hey, Pinkosh.
You know, I think one of the physics teachers at my college said he had Surway as a teacher, which I thought was kind of cool.
Ooh, that is cool. Yeah. And hey, Tipion. So this is this like I'm kind of feeling like maybe for DEDT we need to like think of it as like DDT of E and then E, like we have to use Gauss's law on that. I feel like it's maybe the wrong thing, but oh wait, well, I wanted to plug something in for E relating to Q, but that's not maybe straightforward. Yeah, Dipiana, I was on vacation.
Yeah, I got a book by Halliday and Resnick as well. That's a nice book too.
Oh yeah, I remember you mentioning that. It's a much like a gentler one, right?
Yeah, it's still pretty good though.
Mm-hmm.
Actually, the text I have is just volume 2 of it, which is just electricity and magnetism.
Oh, cool.
Yeah.
Dipiana, I have no clue how to do that, so sorry.
So we got a spherically symmetric shell and a spherically symmetric current density flowing inwards. Charge on the shell increasing at a constant rate. Yeah, and you're saying like maybe find the electric field using Gauss's law somehow?
Yeah, I mean, guess I don't quite know what we're expecting to get. It's bad this is a 1-star problem, and like, I'm not sure how to
Maybe
start
all
it.
we have to do is, yeah, maybe all we have to do is somehow define the J and the B and the E and show that if we plug them into that equation that it works. I don't know.
The J, I mean, what would those be though?
Well, that's a good question. I feel like the J is going to be okay because they say it's spherically symmetric and constant. And the E should be the E should be spherically symmetric, right?
Yeah.
What about the B? It's always a magnetic field where I start to lose my mind.
I assume that the magnetic field of something like this is going to go around in circles. Joven, yeah, if you want to like give us a hint to get us started, that that's fine. Maybe don't just like blurt out the actual answer, but
Doesn't it feel like the B might be 0? Or is that just wrong?
I don't know. I guess if it's sticking onto the shell, I guess there's not a current. The amount of charge is changing. Well, I don't know. I'm kind of wondering how to take the divergence of each side of that equation they provide, and I think they do that as part of their discussion.
Oh,
Or maybe not. Oh. Um,
whenever I think about B, I want to use the right-hand rule, but I don't know how to use the right-hand rule when it's like every one of them's coming into a sphere.
yeah, I was just figuring it should be in a circle because I think like the electric field and magnetic field always have to be perpendicular, and I think that can only happen if it's a circle. That was my only thought with saying that it should be like that. Wait, to verify that it's satisfied, it points outside the shell. Well, outside the shell, so like for J,
Maybe we got to use,
we need to draw like a window. Oh, sorry, what?
I was thinking maybe we can use spherical coordinates.
Yeah.
I mean, maybe you were already thinking of that, but
Is this equation they put here? I assume it doesn't have a coordinate system already, right? We don't have a different version for other coordinates.
well, I just always think of that appendix at the end of the book with all those
Yeah.
different appendix F. Oh, that's right. The curl in spherical coordinates doesn't look friendly.
Oh, yeah, that I feel attacked when I look at this.
Yeah.
Um Okay, well, I think what am I trying to say? If we just look at like a snapshot in time, this like spherical shell is basically just the spherical shell from like chapter 1, like in electrostatics, basically a point charge.
Yeah.
And we're working outside of the shell. It's like, in that box there or something. So as far as like that box is concerned, it's just a point charge with whatever amount of charge Q. And that's increasing at a constant rate, dq dt. I'd expect dE dt to then also be some kind of like linear, like just like a constant, I guess. Hey, hourly dose of internet, yeah. Can we make a comment about J?
What are the units of J again? Is it like coulombs per square meter?
Um,
Amps per square. Is that what it is?
I think it might be
Coulombs per
amps
second
times
per
square
square meter.
meters.
Oh, times.
The main goal of the question is to show that even a complex case like spherical flow, Maxwell's equation is still valid against spherical electron. Oh, okay. It's good to know to keep on. What about currents in chapter 4? Oh no, it is amp per square meter.
That sounds right because it's a density, right? So I think sort of divide by yeah, divide by something.
Joven starts with charge conservation using the continuity equation, and that's the. Is that the divergence of J is 0? No, divergence of J is minus d rho dt.
Oh.
So this does. It does favor taking the divergence of each side. I don't know if that shows that it holds, but the book kind of does a similar thing where if you take the divergence of each side of that equation they give us. Oops. I don't know how I did that.
What?
I made that be like transparent. Oh wait, now it's okay. I'm still gonna delete it. Okay. Plus divergence. You can do this like you can interchange the ddt and the divergence in that last term there.
Yeah, they did play that trick, didn't they? I saw that too.
Yeah.
I
So I
saw
mean,
that.
I don't know if this proves that it is satisfied, but like I think we can get some kind of math that works out here. Um, so you can do this. And the divergence of E is that's like the Gauss's law thing. In differential
Oh,
form.
it's gonna be rho. It's gonna be a rho and an epsilon naught, right? Oh, I see what you're doing.
Yeah. So I still don't know if this
Alright.
is like the most helpful thing, but it looks neat. I don't remember if we need a minus sign in there. Probably not.
I hope not.
We want it to
Well,
be
we don't-
0, right?
Yeah, we want it to be
Yeah,
positive.
and we don't. Okay. Hey, Pawan. Okay, and so this does give us 0 to match the left-hand side. Question mark? Oops. So that's kind of what I was wondering about doing since I saw this problem, but it doesn't feel like it is verifying it's satisfied. Maybe it does, but I feel like we didn't do anything. But we never used that constant dq/dt rate.
Oh, you're right. We didn't need it.
So that's why I'm concerned about, like,
Oh.
I don't think I actually did all that much here.
Well, what if it wasn't constant though? They said that you can, oh no.
If it's not constant, I mean, I think we proved it in general if it's not constant, because the current, like, the flow of the charge onto the shell must be related to the field the shell produces, because it's caused by the charge that's flowing in, I think is what we just did.
Another thing is we didn't really bring into the solution anything to do with like where we were in space, right? I mean, they said outside the shell, and we could have set up like a radius or something, but where would that have come into the calculations, I wonder? And is it any different inside the shell?
Inside, I think it's just like a chapter 1, like, or there is no field inside a shell.
So inside it would just be like 0 = 0 automatically?
Yeah, because the field isn't changing and there's no charge flowing through it.
Okay.
I assume that there's no curl of magnetic field inside there either. I don't know about that, but well, we're taking the divergence, I guess.
I don't know either.
Yeah.
Actually, that reminds me of something in the chapter where chapter 9, where they were showing an electromagnetic wave, and they were showing that what were they showing? They were showing that if you superimposed two waves that were traveling at the same velocity, but or they were traveling in opposite directions, then you'd get the standing wave, right?
Mm-hmm.
Which yeah, a standing wave, which I think of like, you ever see when somebody, like, two people take like a really long jump rope or something, and they like shake it up and down, and you get like points in the middle where it doesn't move? Yeah.
Exactly.
So I was thinking of it like that,
two
like
people inside it. Yeah.
Yeah. Yeah. So a standing wave, and then they said if you pointed it, or if you what were they talking about? They were actually talking about a traveling wave that would come into a perfectly conducting surface,
Mm-hmm.
and it would get reflected off of it. And I don't know, this just made me think of that. Like, I guess this doesn't really have anything to do with it, but it was thinking about it being 0 inside and existing outside, you know. And then they said, in that case, when it reflected off the surface, I was like, well, I wonder what's happening on the other side. But they said, well, I think they said the wave doesn't even exist on the other side.
Yeah, nothing happens, which was like that whole part. I kind of felt stupid for that part. Like, it should have been obvious. Like, I just like the entire idea of a mirror or an electromagnetic wave. I think it's the exact same mirror that we would look at ourselves in. But I still had a hard time like thinking about a mirror in this way.
Yeah.
And I can just like bounce a wave right back like that. And they even made a point where, like, it's not like exactly correlated, but that's why shiny, or metals that are good at conducting, tend to also be shiny, because being good conductors of electricity and reflecting waves are kind of related.
Yeah, I noticed that too.
What if we write Ampere's law and Coulomb's law? Oh, that's a thought. so well, Ampere's law is just the first part of this equation, right? Del cross B is mu naught J. And then I assume Coulomb's law may want the differential form of Gauss's law. I mean, I don't know. Is that what we just used though? So I don't like that I'm like mixing dels and non-dels. What? Oh.
So basically you just showed that if you take Maxwell's equation and then you take the divergence of both sides, it works, right? So
Yeah.
is that enough to show that the equation itself is fine? Wouldn't there be cases where we could have something that wasn't true, and then if you took the divergence of both sides, it would become true?
I don't know.
I don't know either.
It's for the outside, so it can be route B equals mu non-zero J plus m mu. Integral form for Ampere. Let's see if I can do this off my head. Is it mu non J still? No way, right?
I hope my forced air heating over here is not noisy.
No, I can't hear it.
It just turned off, but it's going to be turning on again. It's cold here. It's 29 degrees here.
Oh, dang. Okay.
29 degrees, and we got snow, and we got a travel advisory at the moment. It's going to be snowing for the next 24 hours, probably.
Jeez.
Yeah.
Uh-oh. I'm cold enough, and it's only 64 right now.
Oh, 64. That sounds nice.
Yeah.
This is the first snow of the season here.
Oh, nice. I've seen snow maybe 3 times in my life. I want to see it more.
Oh. Yeah, it's nice.
I bet it gets old if you have to like live with it, but it seems cool.
Yeah. Until you have to shovel a lot of it, and it's like, oh man.
Yeah. I'm gonna do just like the first sentence of the answer because I feel like I'm not even on the right track right now.
Yeah, I'm just concerned, like you said, about this DQDT, but I don't really know what to do with it.
Yeah.
Unless we can somehow come up with, I mean, unless we have to do all this work, like try and get the electric field as a function of time, like say at time 0 there's no charge, and then find the charge on the surface as a function of time, and then find the electric field as a function of time and all that. But I don't think we have to do all that, right? And I wouldn't know how to find the magnetic field anyway. I just don't know how to find it.
Yeah. Jovan is saying to take a circumference around the sphere, and you'll get a B who is a vector in theta. Okay. Like, and that's gonna be like theta hat. So I think it.
Here's why I don't understand that, because I mean, you're saying we could get a circular, the magnetic field would be a sort of a cross section like you've drawn, right? You're saying the magnetic field vector would be sort of following a circle around it, right? Going at right
Yeah.
angles through those green arrows. That should be showing you what I mean here, if I remember how to use this.
Oh,
Yeah,
sorry,
so
forgot to
like coming
like
around
that,
like
yeah.
this, right?
I don't know
But
the orientation,
but here's the thing. Yeah, well, I don't either, but here's the thing. Like, if it's a sphere, if it's spherically symmetric, then what if we just rotate it 90 degrees and we're looking at side on now, right? Well, then
Yeah.
wouldn't it be coming? Well, then it'd be going like this, right? Like North Pole to South Pole, like that.
No, I'm imagining like the magnetic field is spherical, I guess.
But how could it? That's my question. How could it be spherical if it's like traveling tangent to the sphere, right? Like as you've drawn that arrow there, it's going to be tangent to a sphere. If I rotate the sphere 90 degrees, it's got to be tangent to that sphere as well, doesn't it? By symmetry of this problem. And then it becomes like the fuzzy tennis ball problem, right? You're trying to like comb all the hair on the tennis ball, and how do you do that without having a point where there's some kind of discontinuity? Does that make sense what I'm saying?
I guess I'm not sure why there would have to be a discontinuity. Or I don't know the fuzzy tennis ball thing.
It's kind of like if you imagine that sphere to have like hair on it growing out, and you want to comb the hair down, right?
Yeah.
And you try and comb it all down, there's going to be some point on it where,
Oh, where it all comes from.
yeah, what is that problem? I forget it.
I'm imagining like
there's
the thing that everyone has at like the top back of their head, where like their hair like comes out from.
Yeah. Yeah, same kind of problem here with the magnetic field. And if the whole thing's spherically symmetric, I don't understand why there'd be a point like how would you know? How could there be a point like that?
I wonder. Maybe the shell doesn't produce a magnetic field. Because the charge on the shell, I assume, isn't moving, or at least we can pretend like it isn't.
I wouldn't think it'd be moving once it got to the surface of the shell, right? It would just like kind of sit where it landed.
Yeah.
So
I assume that.
So if B was zero, I mean, if B was zero, then what would that mean? That would mean the mu naught J would have to be the negative of the mu naught epsilon naught dE dt.
But aren't the green arrows that I drew to represent the current going to produce a field, magnetic field?
I don't know.
Yeah, that's the.
Every single one of them, I kind of think of it as if it's a wire coming in from some point out at infinity, right? And there's an infinite number of wires coming in from infinity towards our sphere here, our spherical shell. And if you come along any one of those wires and you try and use the right-hand rule, you can get a magnetic field curling around that straight wire, right? But if you got an infinite number of wires all coming in, then don't all those little magnetic fields kind of just cancel each other out? Like the wires next to each other in between, like they all just cancel out?
Oh, maybe. I guess so. I don't know what else would happen.
Kind of like, here we go. Let me try and draw a picture of it. See if I can, I got my pen backwards. So.
Oh, is it pronounced Hoven? Oh, sorry, Fenbox. Go on.
Hoven means young.
Yeah.
So if these were all let's say I had an infinite grid of wires coming in towards the sphere from out at infinity, right? Then if I had, can I change the color? I don't know how to. Oh, I can. There we go. So if I had all these little circles going around.
Zach, thank you.
Each one.
Welcome in. Sorry for $10.
So so I'm just going to have a circle around each one, right? Now imagine every one of these circles has the same, the current's flowing the same direction through each wire. So every one of these little red circles is a magnetic. Should have made them blue. I don't know. Blue feels more magnetic than red. So what I'm saying is if they're all going like this,
Mm-hmm.
which way is that? Counterclockwise.
Yeah.
Then every point where the two circles are kind of touching is going to be interfering, right? Like if I had two of them next to each other like that, this one where they cross, they want to go against each other here, down and up. Right? And if I had another one above this one here, then where they cross, they're going to interfere with each other as well. That's just how I'm thinking of it. I don't know if this is right.
Okay, that seems reasonable.
Hey, Zach's here. Hey, Zach.
Yeah. Hope your stream was good, Zach. Thank you very much, and welcome to everyone hopping in here. Right now this is me and Finbox fan and voice chat just kind of working out some problems from a physics textbook. This is the last chapter that we're going to be doing as part of the group. It's on chapter 9 for Maxwell's equations. We're going to a couple of meetings on it, but this is like our kind of like end cap. I hope your stream was good, Zach. And my voice is a little bit messed up, so that's why it sounds weird right now, but yeah, thank you.
So I'm thinking of a sort of a grid of wires like that, except instead of all being, parallel, they'd all be kind of coming in from into the sphere in the middle. But still, if you kind of looked on any little close section of that spherical shell, they'd all look like they were coming in parallel, right? Once you got really close to the shell. I don't know if this holds.
I mean, I don't see the issue with that. Hovind is saying that, I don't know, Hovind seems to be expecting I guess like you might call it a spherical field, but yeah, I don't know how you overcome that like problem that you point out. And I kind of like your argument that you just made there that magnetic field is probably canceling.
If we had a magnetic field that was spherically symmetric, right? And if it had to be at right angles to so does it have to be it has to be at right angles to the electric field, right?
Mm-hmm.
I think that's true. And if the electric field's radial, it makes sense that the electric field would be a radial field, right?
Mm-hmm.
I'm thinking of it as like going out against the green arrows that you drew.
Yeah.
Yeah, I don't know where I'm going with that. I'm just trying to see why B would be 0. But it probably isn't. I'm probably wrong.
I mean, I feel very confident that dE dt term should be non-zero. So I mean, I don't know. I think it's a lot of time for one star. Maybe I'll just look at the first sentence of the answer.
Yeah, why not? Why not? We gave it some good thought.
B is not 0. Current is moving. But put the sphere in the center. Outside J equals 0. Is J 0 outside? We have like, I guess it depends what we're drawing, but like if we have just like an arc like that, I don't think J is 0 through that arc. I mean, arc is a bad word, but like a rectangular arc, I guess, or something two dimensional. That's like an arc. A portion of a sphere. Wait, keep on. Am I misunderstanding the problem? I thought the current is outside the shell, coming towards the shell. Jahu, thank you so much. I really appreciate that, Jahu. Thank you. I think the current only exists outside the shell. From my reading the problem, keep on.
Yeah, I was understanding it as you are, Don. I was thinking of these as the current density coming in from like infinity,
Yeah.
radially inward to a spherical shell.
Because they say to a spherical shell, not like from.
Classic SpongeBob.
Yeah. I'm doing it.
Yeah, go ahead.
Just a little bit of the answer. The magnetic field due to a spherical symmetric current density is 0. Okay. So that answers that question.
Really? So B is 0?
Yeah, so I guess we should have 0 on the left-hand side. And so we need to justify why the two terms on the right side cancel. I think it's going to be the problem then.
Okay. Well, now we're in business, I think, because can't we just, I mean, if we really wanted to, we could just get them as functions of time, couldn't we? They're going to be like radial. The J is coming in and the dE dt is going out, right? The J would be coming in towards the shell and the dE dt should be going out.
Yeah.
Because the field's getting stronger. So couldn't we, I mean, if we wanted to, couldn't we set it up as some kind of differential equation, like say the shell is uncharged at time 0 and pick some constant for J. Well, let's see. If the charge increases at dq dt, we should be able to find out what J is, right? I mean, we could give the shell a radius. We could find out what its surface area was. If we wanted to, we could do all that stuff.
I think there should be a simpler way, though. I think you're right.
Yeah, there probably should be a simpler way.
Like, I feel like we should be able to just logic out what J should be. If we draw a spherical shell for the current to pass through.
Okay, you're thinking like a Gaussian surface, like outside the sphere?
Yeah.
Yeah, I like that.
The current passing through this. It's something divided by 4 pi r squared.
Yeah.
And what's on top should involve dq dt. Or
Yeah.
I'd like to make it involve dq dt. It is, oh wait, it is just dq dt, I think. Because it's amperes per
yeah, coulombs
meter
per
squared.
second, right? That's okay. Okay.
Kevon seems happy about this. That's a good sign. I hope I'm saying that right, by the way. And so I can relate E and dq dt. Or maybe just E and Q.
Well, if it's 4 pi r squared, you're using a radius of r, right? So that should give us some relationship between E and
Coulomb's
E
law?
and yeah.
Like Q of T over 4 pi r squared. Maybe need a minus sign somewhere in here.
We need a negative somewhere, don't we? Well, they're
Oh,
vectors,
epsilon
so
not as well. Oh, yeah, maybe that's where the minus sign comes from.
yeah, because one's pointing in and J's pointing
So
in.
we can
and I
make
think
one
E-
R and one negative R. I guess J is negative R hat.
Okay.
Because normally R hat points out.
Yeah.
Okay. And that gives us exactly what we want.
Well, you're done, right? 0 equals 0.
Okay. That I like.
So that B was 0. Ah,
They said this in section
I couldn't see how it could
9.2.
not be 0.
When did they, at the end of 9.2, they apparently said that.
Really?
Huh. The magnetic field of any radial symmetric current distribution calculated via Biot-Savart is 0. Huh. Consider the radial line through a given location.
Oh, I'll be damned. There it is. You're right.
Oh, it's basically the argument that you made, I think.
At this location, Biot-Savart contributions from a pair of points symmetrically located with respect to this line are equal and opposite. Oh. So they're talking about what? The ones on opposite sides of the sphere?
Oh, maybe they are. So, yeah, if you...
Oh.
Oh, they're saying like, if you have like a... Oh, this is going to be annoying to draw.
I remember not really understanding this paragraph when I read it.
I think what it's saying is that if you have a magnetic field like, or wait, what type of field is this? A J field.
Current density.
Yeah, like that, and you choose this point as your point to calculate the magnetic field at. Apparently, the current from here cancels with the magnetic field from there cancels the magnetic field from there. I think that's what they're saying.
Okay.
Does that right-hand rule work out? Yeah, because they're going in opposite directions.
Yeah.
Okay. Huh. You'll look through the rest of the answer just to be safe, but
Yeah, you think we got it? I guess we got it.
I think so.
The heat just came on. It's not noisy, is it?
No.
Okay.
Should the
I can
points
mute as it
outward.
gets noisy.
No, it's all good. Yeah, I think we did it right. I think the same argument as we made. Okay, well, that was just an hour for one star problem, so off to a good start.
Well, to be fair, I was 10 minutes late, so it was,
Oh.
50 minutes maybe. Oh, but it's
There we go.
5:06. Yeah.
Oh gosh. Oh, I remember seeing this one. You have a headache, Open? Yeah, same. This one might be a little bit long, but Now that I look at it, I was just grabbing all the 1 and 2 stars.
Okay.
I just at least like read it though. There's a very similar problem that we did in chapter 1. This might not be too bad. I don't know. Get the exact bios of
Well, part A might not be too bad.
yeah.
Oh, part B says you can invoke the result from problem 115. I wonder if we did that one.
I remember it. I got screenshots of it.
Oh, okay. Yeah, you just said this was similar to a problem we did in chapter 1. Is that what you said?
Mm-hmm. And I grabbed the result of this. The second one is the answer to 15, or like the chapter 1.
Okay.
Hmm. So does the Q point itself contribute a magnetic field? I think no, because of what we just did in the last problem, or that same fact. Pen, thank you. Hope you've been doing good. I saw a bit of that linear algebra thing that you were doing. It looks cool.
Yeah, I was trying to watch a linear algebra lecture while I was trying to cram chapter 9 in.
Oh god.
Yeah. Yeah, that was me.
It's doing math on hard mode.
Well, it's my own fault. You know, I spent all day yesterday when I could have been studying and I was just doing Sudokus.
It's a good use of time too.
Yeah, I think that linear algebra is going to be good.
Awesome. Derhohi, thank you for the follow.
Use the Biot-Savart law to add up the contributions from the different parts of the wire. Oh, I see what you're saying, Don. So you're saying like that point at the end of the wire might be a little bit different from the rest of the wire.
Yeah, I'm hoping we just neglect it.
Yeah, once the charge gets to Q, it stops moving, right? So if it stops moving and it becomes like static there, doesn't that not give us a B field anymore once it stops moving?
I think so.
Okay.
I hope so. Because you are varying the amount of charge in it, but I feel like it still shouldn't make a magnetic field because at any like moment in time, it just looks like an electrostatics problem. I feel like. I think that's a bad argument to make, but
I like it.
okay.
So then we just have to integrate along the wire.
Yeah.
How does this BO-Savar thing work again? So R is the distance from the point on the wire to the point on the circle.
Mm-hmm. So like that.
And R hat is, what the heck's the DL? DL was the little,
Length of wire.
yeah.
Or just like, I think it's a unit vector that points along the wire in the direction of current. So it's like that.
Yeah.
Yeah, 1 second, Hoven. Struggling with arrows. Okay. We're working on part A here. Derholi, first semester mechanical engineering from Switzerland. Awesome. Yeah, so
Nice.
yeah. This is a reading I've been doing on Saturdays. We're towards the end of it here. We're very deep into electricity and magnetism book. But working on this problem that's on screen right now. This is we're doing like Maxwell's equations. And since you seem like you might be interested in your first time chatter, let me. There's a whole bunch of math streamers out there he may be interested in watching as well. I'm not the only one. So whenever I see new faces, I just like to let people know that there's a whole like community of us here who stream math and hang out in each other's chats and just talk about math and physics. So I'm here, but there's also a bunch of other people here who may be interested in watching too. Oh wait, so we're not. Oh my god, I was gonna be Savar wrong. We're not calculating around the entire circle, just at any point on the circle.
Right. We just want to find the field at a given point on the circle, right? So, so we could pick a point on the circle and fix it, but we just got to integrate along the wire now.
Right.
So, what's the best way to do this? I wonder. Put the origin at the center of the circle, maybe.
I was looking at the Q and go from negative infinity to 0.
Negative
Maybe it
infinity
doesn't
to
matter.
something. Oh yeah, negative infinity to something. I guess it would be 0 if we could put the origin at the Q. You're saying put the origin at the Q, right?
Yeah, it might not make a huge difference, but
Yeah, it might not make a huge difference.
will be easier.
I think they're both the same.
Yeah. Let me just go with what you thought and do it at the center of the circle here. And so I guess we know that R is equal to B sine this angle I'm calling phi. Oops, that's rho. Yeah, Bios of R is kind of weird to use. So wait, we're crossing R and L. It's not trivial, right?
EL cross R. Magnitude is magnitude DL. R hat's definitely a unit vector, right?
Mm-hmm.
The DL, I don't know. Is that a unit vector?
It's like tiny,
Well,
I
mean, we
think.
could. Yeah, because it's a D, right? Length of DL times. So now it'd be we'll just sine a phi, right? You're saying like this. So that's the magnitude of it.
And so we could do that.
Oh, we gotta
but we
take
have to figure out
we
the
gotta take a
direction.
sine or a cosine or something, don't we? Oh, this is so embarrassing. I'm so bad at this stuff.
I'm not confident what direction this is going to have. Because I don't know, it's just weird. Like, I almost won't want to go into the vector components and do the actual cross product.
Yeah, we could. We could.
I don't know if that's wise, but like DL should be like DX 0, 0.
Okay.
And R should be something.
Just sine phi and cos phi and sine phi, right? And
I
zero.
feel like
Cos phi, sine phi, 0.
do we even need the ink? Like, whatever our X coordinate is.
Okay.
Or I'm just thinking about it in terms of like components. Like it has that entire length
Yeah.
as the component, and I'm putting a negative because we're in the negatives. And then the Y component is always just B.
But the R hat would be pointing to the right, wouldn't it?
Oh yeah, it should be.
Doesn't it? It points from the wire to the point, doesn't it?
Yeah, maybe we don't want that negative.
Yeah, I would say make a positive.
Yeah, okay. But like other times they just kind of get the magnitude and they work out the direction intuitively. So I'm not sure if this is like the best thing to get into, but I don't know what
think
else
it's
to
fine.
do. Okay.
Well, by right-hand rule, shouldn't the magnitude just be coming out in the positive Z direction at that point? I think.
I'm concerned that I don't think it'll be exactly the same. It's just like if the wire went all the way through. The farther away we get, I don't know. Wait, if this isn't enclosing any current, shouldn't there not be a magnetic field?
But it's close. But it's close to a current, right?
I guess so. Oh, this is not a unit vector.
Right, you'd have to divide it by square root of x squared plus b squared.
This feels like overkill, but I really don't know.
I don't mind. I like to see it.
Okay. This cross product isn't so bad. Because I guess we get two components, don't we?
I think it's just a k.
We don't get a J?
I don't think so. Because you got 2 zeros under the k, don't you?
Oh, okay, yeah. Good. I guess I'm not. These are hats, aren't they? I don't know if it matters, but for those, but. So maybe you were right then. If it's only in the K, maybe it's only in the Z direction.
Yeah, I think so. And I think it doesn't matter as we integrate along the wire, every little piece will just give us a Z component, I think. Well, that's just what you just showed actually, isn't it? Because that is what you just did. You did the DL cross R. So as L varies, as X varies,
Okay.
this is what we get. Yeah.
I was expecting it to like flatten out in some way, I guess, or get a little angled, but I guess not. Whereas I thought we'd get some kind of J component, but okay. I guess we're good.
Well, if you picked a different point on the circle, you would get a J component, right? So as you go around the circle, we're going to get some kind of a magnetic field that goes around that circle. But because you kind of pick the top point on the circle, we'll just get a yeah, I think that's right. The top of the circle, we get a Z, and at the bottom of the circle, we get a negative Z. And on the point of the circle closest to us, we're going to get a negative J, negative Y.
I guess so.
Yeah, so like up here, it goes that way. Then here it would go down, there it would go left, and in the back it would go up again. So it's kind of always going that around that way.
Okay, yeah, that's fair.
Okay, so now that you got that, we could plug it back into the dB. And then integrate it with respect to X, I guess. Actually, wait a second now. What about this? Oh, no, it is. No, you got it. DX. What happened to the DX there? That's right. We need a DX in that.
DX. Oh, yeah, we do. So I guess this was doing it the hard way. We probably should have obtained this from we probably should have obtained this from like a parameterization, but we do, I guess, have DL cross R now, or R hat.
Yeah.
So Bio Sava, mu naught I, which is constant. Four pi DL cross R is B over root squared plus B squared dx times 1 over R squared is just x squared plus B squared. And we're integrating from minus infinity up to, is that B tangent theta? Or wait,
Cotangent, B cotangent theta.
tan theta, it might be cotangent, yeah. Opposite over adjacent, I don't know what to call that length. A. I guess it would be cotangent, yeah.
We probably want a negative on that too.
Oh yeah, yeah. Okay. and this
Trig
would
integrals.
be, more like integral table. That's what I like here, at least.
They got this in the back in the integral tables, this form.
This is a common one, I think.
It looks
Just-
pretty familiar.
Yeah. I think we've encountered this one before.
Yeah, I'm sure we did. Should have it memorized by now.
Physics and depression had some crazy like facts memorized when I asked him about any thing once. He had like the average value of sine over 0 to pi memorized, or like stuff like that. You can use it to solve integrals quickly with
You
the
know, that came
average
up in
value
this-
of the theorem. Oh yeah, it
Yeah,
did.
that-
Yeah.
At the end of this chapter, they're talking about the power carried by a wave, and they did the average
Right.
of sine squared from 0 to 2 pi or whatever.
Okay, got it.
Yeah.
ln root x squared plus b squared plus x.
This physics is making me hungry.
I was just thinking
I don't-
about food
I don't know
too.
what it is.
I had an Albert burger for the first time in years a few days ago, and it kind of gave me a craving.
Oh. You know, I think that isn't that only in California? I don't know if
Yeah,
I've
they
ever
have
had
a
that.
few in a couple like bordering states, but it's mostly just a California thing.
I may have been there once. I don't remember.
Oh, okay.
Not to California, to In-N-Out Burger.
Yeah. It's pretty good.
Yeah, they're good, really good things about it. Aren't they one of those places that's supposed to have like a secret menu?
They do. It's not very secret, but they call like a secret in quotes menu. I think they actually advertise it now.
Open secret.
It was a lot. better of a secret before the internet was a big thing. This seems like an annoying limit to do for the second part of the limit here. First bit, we can just plug in. At the risk of messing up mental math, we should get b root cotangent squared theta plus 1. I hope that's a Pythagorean identity.
Oh, it's got to be, doesn't it?
The second ln, I'm not quite sure what to do with. We're in infinity minus infinity. Inside an ln. Oh wait, but that's not the worst limit. I forget the trick, but like I went to Wolfram Alpha. Cotangent is cosine over sine.
Oh, I just did that over the left. Yeah, it's
Yeah.
cosecant.
Okay. Cosecant. Good.
Yeah. Cotan squared plus 1 is cosecant squared.
Oh, there we go. I'm gonna Wolfram Alpha this limit.
All right.
I forget the exact trick to do it.
Wait a second.
Oh, you probably
That's
just
gotta
factor
go
out an
around
x in L'Hospitals.
Doesn't that have to go to infinity? Yeah, how could it not? Well, that's not good. We don't want this to go to infinity, do we?
No, the minus, we get infinity minus infinity. I will just
Oh, it's
do it by hand.
it's a minus infinity we're going to. Sorry.
No, it's all good.
Yep.
I think I might remember the trick.
Oh, you know what I bet you the trick is, Don? I bet you the trick is rationalize the numerator. So multiply by
Oh,
square root
yeah.
x squared plus b squared minus x, top and bottom. I'll bet you that'll get us there.
I think I heard it called like the binomial conjugate or something like that.
Yeah.
Which is a nice word.
I always just thought of it as rationalizing the numerator because you learn as a kid to
Yeah.
rationalize the denominator, and I was like, well, this seems like rationalizing the numerator.
Mm-hmm. Yeah, Kevon, that makes it a lot. That does make it tricky. Okay. And this is good because we get 0? Because the denominator is going to positive infinity now, right?
Yeah, good.
In ln of 0, oh no.
Oh, well,
This
we
is
don't
all
want
inside of an
zero.
ln.
All
That's
right,
not good.
let's,
Let's make sure I didn't make a mistake. Ah, that's not good.
Oh, but okay, well, E to the, no, we can't do that, can we?
There must be an issue with the way we set it up.
You got that antiderivative, was it ln of that whole thing, like square root x squared plus b squared plus x?
Yep, it's all inside the ln,
Okay,
unfortunately.
yeah.
Oh wait. Oh my god, I looked at the wrong one. I did it for root x squared plus a squared, not the 3/2.
Ah,
Oh my
okay.
god, it's completely different. Ugh.
Where do they have all that stuff? It's in one of the appendices, right?
K, the last one.
Okay, okay. There's a lot of good stuff in Appendix K.
Mm-hmm. Okay. X over b squared root b squared plus x squared. Okay, hopefully this one works out better. It's a ratio, so hopefully it becomes 1. Well, actually, I guess, no, now we want it to be, well, it can be whatever it wants. Okay. It should just be 1 over b squared, I think,
Yeah,
because the degrees are the same.
yeah.
On the left side, minus cotangent theta. Okay, we can cancel a b from here and here,
Yeah.
but then we can factor out a b and it gets rooted, so we get a b squared back out.
Okay.
And then 1 plus cotangent squared is cosecant.
Yeah.
Oh, that is minus infinity. Does that give us a negative sign?
Good catch. Good catch. Yeah, it does. So it'll be plus
Yeah.
1 over b squared.
That, I think we're going to get 0, or no, not necessarily, but I can't untangle the cotangent and cosecant in my head. B squared comes outside.
close over sine over 1 over sine. It's just cosine, I think.
Oh yeah, you're right. Okay. Negative. Oh, and it's B on the top as well, so that can cancel. Cosine. And there's a 1. Okay.
Well, that's nice, because look at what you brought over from the previous chapter. It had a 1 minus cos in it as well.
Oh.
That's kind of encouraging.
Yeah, you're right. So what's our limiting case here? Like, if theta approaches 90 degrees, we're getting just a regular wire, which is perfect. If theta approaches 0, we get 0 because we're very far away. So that seems reasonable.
Theta approaches 0. I see what you're saying. You're saying that our circle's very far away from the wire.
Mhm.
Okay. What did you say? If theta's 90, it's like we're going right to the middle of the circle.
Yeah, it's like a normal Ampere's law.
Okay.
Suna, thank you. How's your stream? Welcome in, everyone. Okay. Well, I feel good about this.
So that's part A.
Yep.
So we're doing this thing 3 ways. So if we get the right answer, that should help us with B and C.
Mm-hmm. Studying a bit of biology. Ooh, cool. Okay, so we're working on this E&M part right now. We just did part A, and I think we got we got the right answer. We're working on part B now. So the left side, I think, is B 2 pi r. Oh wait, what is the normal? So Ampere's law supposed to be 4 pi or 2 pi, or just like the field for a wire. No, this is a Benbox fan in Discord, and he's just helping me out if anything.
Yeah. Okay. I'll take that. I feel like I've been holding the team back for about the last, 6 chapters, but I'm doing what I can.
No, you've been super helpful.
Hey, Suna.
Where the heck do they say the field due to a wire?
Yeah, we're struggling with physics here.
I'm worried that we're off by a factor of 2 right now.
Really?
Or maybe we're okay because we're not. Well, So I think the magnetic field due to just a wire has a 2 pi, not a 4 pi. And I would think that if theta is pi over 2, then we should get, well, it is only half a wire.
That's what I was about to say. Yeah, half infinite wire. So so when you think of, you were saying like let theta equal 90, right?
Mm-hmm.
That means the Q is right at the center of the circle, but we still only have half the wire. like the
Okay.
left side and not the right side. So it feels like the 4 pi might be right then.
Yeah. And they do, yeah, and in that chapter 1 problem, they do have a factor of 1/2 there. Okay, maybe we're okay then. Keep on. In this method, we use the integral form of generalized Ampere's law, which also includes displacement current. Okay.
And it says we want to choose S to be a surface bounded by the circle that does not intersect the wire, but is otherwise arbitrary. So it feels like we could use the trick from chapter 1 where you take like a spherical cap. I mean, we could do that.
Yeah, we could even just do a flat circle too, I think, for the surface. I guess like part A or part B in that chapter 1 problem.
Yeah, okay. Is there any one that's easier?
I remember working on that chapter 1 problem, I was struggling hard with the spherical cap part. I don't remember it that well though. DEDT.da. It's 2:49 in the afternoon in my part of America right now, in California.
I'm on the East Coast, 5:49 p.m. here.
So left side is B times 2 pi r, oh, B, small b. Oh my god, Suna with the timestamp. It's getting late at night. 2:19 a.m. Jeez. To that timestamp program. Oh, nice.
Don't we just want to work the right side of this equation? Because I think
Do we?
want to, yeah, I would think so. And just try and get the right-hand side to kind of give us the same thing we got.
I was just thinking about how they were using Ampere's law before, where they would, choose some simple line to evaluate it around, and they would always like divide over that 2 pi b per 2 pi r.
Yeah, wait, because in part A, we found a B field at a point on the circle. Okay.
Why does the problem look so simple? They always look simple until you try to solve them.
So how do we put this? This looks like displacement current, isn't it?
Yeah, it is. Yes, Suna. Ordering as like an evolution, like this is like a chapter 1 problem, just using like Coulomb's law on the bottom here, and they're asking like an evolution of this problem about the magnetic field instead of the electric field. Are they going to be sneaky and say that we can take the d by dt out of this? And that's how we get to invoke part 1?
Maybe.
Or chapter 1? That would save us a lot of work if that's possible. Because I don't know how to do this otherwise, I don't think. Let's see if it gets an answer that matches. Hey, boss.
Because the Q is going to turn into an I, right?
Yeah.
Okay.
Maybe I shouldn't divide that over yet. I think it's too early.
Oh, I like this. I think you're onto something here.
Hopefully, the epsilon knots are going away. That's good. We get mu naught I. Theta does not depend on t, so that's okay.
Right.
1 minus cosine theta over 2. And now I guess I get a common denominator and then we can divide over. That feels weird. This feels slightly wrong now.
It's not quite getting us where we want to be.
We have a 3 in here.
So it's that extra mu naught I term. If that wasn't there, we would have got the same answer.
Yeah, but we just delete it entirely. That'll be nice.
Well, wait. If we choose S as a surface that's doesn't intersect the wire, then can we just say I is 0? For that.
Oh, I enclosed. It's not the same I. Yeah. Because
Is that how that works?
oh, that's the entire point of the problem. I was asking why we wouldn't get 0 if we're not enclosing any current. But that's the entire idea of displacement current. I think it's 0. Yeah.
So you're saying the I in the mu naught I term is like the I enclosed by our surface, right?
Yes.
Because then it will be 0.
Yeah, because like this piece is just the regular Ampere's law that we know and sort of love.
The regular Ampere's law that we're supposed to know, and some of us know it, but some of us don't know it. So
Okay, so We can say that
Yeah,
would.
I wasn't realizing this was going to be 0.
Yeah, I mean, I didn't either. Of all those, bring
So
those
we're good.
over.
I think we're good.
Yeah.
Or at least we got 2 answers that match, so they're both right or both wrong.
Yeah. What do you mean it wasn't obvious? I know, Pen. We need to go back and say, oh, it's so obvious. We definitely knew that from the start. This is a recording. We cut all this out. Cosine theta 4 pi b. Hell yeah.
All right.
Now C sounds a little scary.
Yeah, what's C telling us? Let's S intersect the wire. Oh, what?
Yeah. I feel like the I enclosed is still 0 though. Because
No, surely if it intersects, it would be I, wouldn't it?
but Ampere's law only depends on the line integral, and that still goes around that same circle. And and so in theory, it should be the same exact thing, I think. I wonder if they're making the point that it shouldn't matter what solid we draw. That would be convenient.
Yeah, okay, this is good. This is a good concept question. But I don't get the concept. It seems like if so Gauss's law is like so Gauss's law, you have a closed surface, right? And you're talking about enclosed charge.
Mm-hmm.
Ampere's law, you have a closed loop, don't you? You have like a
Yes.
closed loop. And then you're talking about enclosed charge inside the loop. Okay, so what does that
Current,
even
but
mean?
yeah.
Inside the loop. So, oh, that's what you were saying. Is that what you were
Yeah,
saying in
because it
part
like
A? Because if you think of that disk as they've drawn it, there is no current.
exactly like we
Right.
want current to be right here. Oh, but it's not. And so that's why displacement current matters, I guess. Because we know there should be a magnetic field there.
So does that mean B and C is really just the same problem? But they're just trying to point that out to us?
I could see that because I don't see how anything would change. Oh
So if we
well,
change the surface S, do we change like the displacement current?
yeah, we should maybe give that some thought because if we have a surface like that, there is a bit of an issue where the current from this portion of the wire isn't interacting in the same way with the current from this portion of the wire from inside versus outside. That seems worthy of some thought at least. Oh, maybe it does. It shouldn't change. Maybe it should change. No, it shouldn't. We're given it's the same thing in all 3 ways. So it shouldn't matter for some reason what surface we draw. Well, is the wire itself contributing to that DEDT term, or is it only the point charge Q? The electric field due to a wire. I think they said it just goes perpendicular to the wire.
Yeah.
So maybe there's a contribution from the portion of the wire that's inside. But it's constant, or like the current is constant. It's not, the field isn't changing with time.
Okay,
So
so
DEDT is 0, I think. Or DEDT from the wire is 0. From the point charge, ideally it's still the same.
oh, I think I see what you're saying. You're saying like think of the current flowing in the wire and then moving through the wire, but then think of all the current massing up at point Q. And you're saying the E field based on the current doesn't change in time, but the E field based on the Q point charge will change
Yes.
in time. Okay. So we only really have to concern ourselves with the charge at Q.
And
Then
that,
couldn't we work out DEDT? Oh,
I mean, I think that is just going to be the same justification as we just did in part B. Because we implicitly already did that by invoking the chapter 1 result. Like that, the chapter 1 result only cared about the point charge Q. So we didn't think about it, but I think we did already neglect any field from the wire itself. And that was okay, hopefully. The only thing that I'm trying to figure out now is what's the orientation of this surface. Because I think you can get a flipped sign. Depending on how it's oriented, right? Like, how do we define that A vector? Hey, Ben. Ben, it was so awesome. Like, I want to go back to Japan. Is that a kidney? They've been calling it like a balloon. They've been calling like just generic surfaces balloons for some reason, but it does look like a kidney or a bean or something. No, we didn't do the deer park. It's by Kyoto. We spent the day in Kyoto, and it's like a little out of the way.
Did you learn
Um,
some Nihongo when you were over there?
what's that?
Nihongo. I think
Like,
that means Japanese in
oh,
Japanese. I think that's how
uh,
they say it. Like
I
Espanol is Spanish.
oh, I didn't even realize that. I learned a couple of phrases. I did get them mixed up though, where sumimasen I think means excuse me, and gomen
Yeah,
nasai
sumimasen.
means sorry. But I got them crossed up, and I started saying to people "gomaimasen," and I put it into Google Translate, and apparently it means more rice, please. So
Well,
I bumped into
that's
people and
perfect.
asked them for more rice, apparently. But other than that, I feel like I did a good job of learning some phrases.
Yeah, I took one semester in college, and I remember we learned sumimasen
Oh, nice.
and konnichiwa.
Hmm. Um,
Sayonara.
Okk is Czech. I like a restaurant.
We learned o genki desu ka?
What's that?
That means how are you?
Oh,
How are you
okay.
doing?
And then you can't understand whatever they say back to you unless you learn those. But
Yeah, yeah.
um, Mercer isn't great. He changed what's in the pen sum. Oh, geez. Abstract linear algebra. Oh my god. Yeah. Good luck, Ben. Um,
So this question. So this question.
so I feel like I understand what's happening here, except for the question of how is this thing oriented, like the actual a vector. Like, is it like that
Well, I don't know. It's either
or
inwards or
like
outwards.
that?
I don't know. But if we get
Yeah,
it wrong, we're off by a negative sign, right?
yeah. So I assume it works out in some way. I just have a hard time figuring out which is which.
Yeah. Didn't they say it was always like the unit normal outwards?
I guess, but like I'm like if it's like this. Oh, that's weird. If it's like this in this situation, then if we do the part B case where the surface is, pretend like that,
Yeah.
like we want it to flip directions. So that's the part where I'm not clear on in order for this like match up.
Yeah.
But we could just look at the answer and see what they say.
Well, we could at least check A and B if you want.
Oh yeah,
See if
okay.
we're
I'll be
see if
careful
we
when we're
got the right.
scrolling.
See if we're-
Number 3.
This is a good question, though.
Yeah, I feel like I understand a little bit about displacement current, or at least like how it works a little bit. Um, mu naught I over 4 pi b 1 minus cosine theta. Oh, please. I think that was right, right? Okay,
We've got U naught I over 4 pi b times 1 minus cos theta.
good. Okay, so we got the final answer right. Let's see if we got the setup stuff right.
Cool.
Oh, they choose that. I don't like that choice of angle, but fair enough. They get a completely different integral, but that's okay because it's the right result. And B field is tangential to the circle, like you said. Nice. And for part B, mu naught I term is 0. Because the current does not pass through the surface. Oh, that's not good. Okay, so maybe we do need to do... Really? Okay, we're gonna have to rethink part C, I think. Because that blows up my idea entirely.
So are they saying in part C that we do have to, the I won't be 0, right?
Yeah.
See, I guess I still don't really get this. I don't think I understand Ampere's law.
Yeah, I don't know how... That's really unexpected to me. I don't understand it either, evidently.
Gauss's law I understand because you got a closed surface, so you got the inside and you can work on how much charge there is inside it. But if you got just a loop for Ampere's law, just a loop, like a two-dimensional, object, then if you're free to define a surface that just has that as a boundary, then couldn't you push that surface around and change whether there's current flowing through it?
Yeah, I agree. That doesn't make sense.
Maybe that's the whole purpose of this displacement current thing, right? That's probably
It compensates,
the
I
whole
guess,
purpose of,
for that.
yeah, I guess. Because maybe that's kind of what they were showing us in that picture that I called the doorknob, where they had like the circle, but then they pushed that thing around and made it into the doorknob shape, and the doorknob shape wasn't intersecting any current.
Oh. Huh.
I think that's what's going on here.
So I wonder what's gonna be like that. Like initially for part B, we had the extra mu naught I term. It was becoming too much. I wonder if
Yeah.
Instead of we're gonna have the mu naught I term this time, but I think we might be subtracting off the displacement current because of the orientation of the surface.
Okay.
I feel like we're still going to have an issue with the sign somewhere, but that feels like what we're expected to do. Vaguely. Well, it's a plus. What happens here? I think we're going to... the cosine is going to flip signs, and that's not good. But other than that, I think this would nearly work.
What about if we thought of something like this? Like this could be a spherical surface. This could be our wire coming in here. This could be our like circle that we were looking at. Oops, Oh, oh no. Excalibur is not happy with me.
Oh no.
Because what I'm thinking is we could think of this as two different parts of the same spherical surface, right? Like, so the dotted line here is the well, didn't come out too well, but that dotted
Oh.
circle is supposed to be the circle we were given, right?
Mm-hmm.
And then think of this over here as like the cap, the spherical cap from the chapter 1 problem we did. Is that making sense? That's and
Yeah.
then the rest of the sphere could be like what we're going to do in part C now. So the cap could be from part B, and then the rest of the sphere could be like the part C. I'm just wondering if there's a way to somehow exploit a spherical symmetry there.
Yeah, just where they sum up to the entire sphere.
Yeah. I don't know. It's just an idea I had. I don't know if it's going to get us anywhere.
I don't know either.
Oh, Q is supposed to be the center of that sphere. Sorry. Yeah, we want Q at the center.
Mm-hmm.
There we go. That makes more sense. EDTDA. So we'd have to find the EDT over that surface area. Yeah, could we do that?
It should just be the magnitude of d dt times 4 pi r squared or 4 pi b squared, or not b. Whatever the radius of the sphere is, right?
I'm thinking of what you said a minute ago, which was the electric field based on the wire is at right angles to it, but it's not changing in time. But the time changing electric field is based on the buildup of charge at the center of that sphere, right?
Mm-hmm.
So wouldn't all the DEDTs be just coming radially outward from that center of that sphere?
Yeah.
Hmm. DEDT. So it's kind of like what we did in part A now. So if I picked a point on this, let's see. R is constant. So can I just say this is 1/4 pi epsilon naught? Come on, Excalibur. Don't fail me now. R squared times I.
Mhm.
Okay, then couldn't we just take that and multiply it by the total area of that sphere minus the little cap that we're cutting off? I got a feeling this is going to work.
Okay.
So now, how do we find the area of a spherical cap? What's the formula for that again? Is this in Appendix K, or do we have to do an integral?
We can do a Google.
Yeah, I guess we could do a Google.
I feel like it's a simple
I know
formula for it, I just can't remember it.
I think that's what we effectively did in the question in chapter 1. I think it's basically the result we came up with, isn't it?
Probably 2 pi r squared 1 minus cosine theta. That seems promising.
Yeah, is that you found that online?
Yeah, Wikipedia has a few versions of the formula. I'm looking at. I can't like highlight on the stream, but in the little like table on the column on the right.
2 pi r squared 1 minus cos theta. Yeah, where theta is that central angle. Okay, good. Okay, good. So
The r, it's going to be something involving b though, like b sine theta or something.
yeah.
No, b over sine theta. I don't know what's good or bad.
Let me draw a triangle. So radius here was b. That's b. That's theta. We're calling this r, right? The radius.
Mm-hmm.
We did this before, so okay. And then the area of the cap was 2 pi r squared times 1 minus sine theta. Is that what it was?
Cosine theta.
Cos, sorry, yeah, thank you.
Good, yeah.
So total surface area is 4 pi r squared, right? So, sorry, my Discord making noise. The area of the bigger cap, the area of the rest is 4 pi r squared minus 2 pi r squared 1 minus cos theta, which is 2 pi r squared times 2 minus 1, so 1 plus cos, is that right?
Right.
So what I want to say is d dt dot dA is I over 4 pi r squared. Is this good? Am I using the same r for the same thing? I think I am.
Yeah, I think it's the same r.
Times 2 pi r squared 1 plus cos theta. So this just gives me a 2 down here. So it's 1/2 I 1 plus cos theta.
This is like the same issue that I was running into with my version of the work.
Now is that going to work? Because we got
Or
to
maybe
plug
it's
it
not.
back.
Yeah, maybe it's
in.
okay.
We'd have to plug that.
Because what is, again, this is the term on the right. Or the second term on the right.
Yeah, so we got mu naught I minus, no, mu naught I plus mu naught epsilon naught times this thing I just came up with. Is that right?
Oh, I think you dropped the epsilon naught, but
I did, didn't I?
this could work out. Which I think it does, yeah.
Yep. You think it's going to work?
I think. Not sure yet.
So what is it? Integral BDS equals mu naught I plus mu naught epsilon naught
Mm-hmm.
times all this stuff. Oops. So these cancel. Factor out of mu naught I. 1 plus. This is not looking. Does this look it's going to work?
Oh, wait, there might be a minus.
Did I miss one?
Just because the result of the integral, I think the A and E vectors are opposing each other. So there should be a minus as a result of the integral.
Oh, I see what you're saying. So, so there should be a minus in here, like in here. I see. So is that going to fix this problem? Let's see.
That's what I think
you're
we
right.
do need
So-
a minus sign. It might work out now.
This is the whole minus you were talking about with the
Yeah.
orientation of it, right?
Exactly, yeah.
Okay. So where the heck do I put that? I just
Probably as soon
smuggle
as
it
you
in,
get-
right?
I mean, yeah, I think it would technically like right there and right there.
Okay. So sort of put it right here. Okay. So then this, I'm going to have to put a minus where that plus
I did
is.
sneak an integral into the thing that you put initially just because I think we needed it.
naught I times 1/2 minus 1/2. Is this right?
Seems promising. Yeah. I think you
Okay.
did it. Because the left-hand side will get what we want.
Because the ds is going to be integral bds is what? It's b times 2 pi b times 2 pi times the little b. Is that what it was?
Yeah.
Sorry, reloading.
Oh, yeah. Excalidra's not happy with this much math or physics.
I think my computer is a little bit. Oops.
Oh.
I'm running it on a kind of an older laptop here. U naught I 1 minus cos. Stop this. 4 pi b. Oh, oops.
Nice. That's crazy we had to go to that, like, Gauss's law argument there. I wonder if the book does it in a different way.
I was just trying to come up with a way to think of getting a surface so that I could use symmetry on it, you know?
Mm-hmm. Um,
Yeah, let's see what they did.
okay.
Did we get the same answer? Mu naught over I 4 pi b.
Yeah, I think it matches.
Nice.
All right, looking at it. What?
I think they had a much nicer way to do it.
Yeah, I'm trying to figure out this part. Oh, okay. Total flux minus the flux from chapter 1 problem, which is basically what you did with looking at different
Yeah,
portions
it's
of the
kind of how
sphere.
it's kind of how it turned out.
Yeah.
But I was thinking of like doing a whole sphere, and they're just saying, well, just don't worry about what they're just saying. It could be any arbitrary surface, I guess, and just think of the flux, the total flux, you know?
Yeah, I guess Gauss's law lets you do that.
Yeah.
We use a particular one though. I guess that's okay. Then it was correct to slap a negative sign on because of the orientation.
Yeah. Yep.
Nice.
All right. Pretty good. We went overtime.
Yeah, this problem was kind of like addicting though. I hardly even noticed.
Yeah, it was good. It was good. It was a good
Awesome.
choice.
Thank you.
Actually, I like this one more than the first one.
Oh yeah. The the first one I don't know if we were overthinking it or underthinking it, but it was a little weird, yeah.
Well, thanks for having me.
Thanks for being here for another week. We had a little break, but hopefully no more. Yeah, I guess 2 more meetings on this. We should hopefully be able to get through all the 1 and 2 stars in this chapter, depending on how long it takes, I guess. But
Nice. You got
Yeah.
any tea at home? Have some tea. Drink some tea.
Oh, I did right before the stream. I might
you?
need to double up after.
Yeah, I got
Um,
some tea right before we came on. I got some chamomile, but it's gone.
oh, nice.
Yeah.
I have this.
All right. Well,
Oh, sorry. Yeah. If you want to go, then please go.
oh no, no.
Okay. Yeah.
What were you gonna
I was gonna ramble about tea. I have this like
say?
throat. The brand's called Throat Coat, and I was trying this. They're like eucalyptus foot flavor. It's not very good, but it does help with throat issues a lot. And that's all.
Yeah, eucalyptus.
It tastes
Yeah.
okay, but I prefer their like other flavor. It's like something weird, like slippery elm. It's called or something.
Oh. Yeah, my mother used to give us eucalyptus tea, I think, when we were kids.
Oh, cool.
We had
Um,
honey lemon. That's nice too.
mm-hmm. Eucalyptus minus foot, or
What
is
does
it
that
hyphen
mean?
foot? I don't know. It'll be either way. Okay. I think there are some questions in the Discord for me to get to. So,
Yeah.
um,
Yeah. Well, nice to see you. Nice to see you back on stream.
thank you. It's good to have a session with you again. So I'll see you around.
Yep. See you next time.
Okay. Let me change my title and category here. These films are so much fun. The last one was hard, but like achievable. Okay, title and category. Switch to the YouTube stuff. Okay, YouTube info updated. Still solving? Oh, nice, Hoban. Sound like you. Oh, eucalyptus foot. No. The eucalyptus foot tea sounds terrible. Any type of foot tea sounds terrible. But I'm sure that, there's probably someone out there who sells that. I'm sure. That gave me whiskey tea to help me fall asleep. Oh, no, that's just whiskey. Okay, there's two problems in Discord from the Viking. I just wanted to get to these and then call it. Assume my voice can hold up. Insulting Ian problem in like 5 to 6 years. Oh god. That's gotta be hard to like get back into it. Had some tea to put my foot in, so that's like foot tea. Yeah, fair. Transmithanol applied to metallurgy. Oh, okay. That sounds fancy. Oh, okay, so we just have to check their work, I think. Come on. Okay, like they're drawing. I'm probably gonna try not to talk as much. Actually, I might just do this off stream. Yeah, it's just chicken work. And my voice is feeling it. Let me just wrap up the stream here, I think. Most of the things, it's going to take a while. I don't want to talk through all this right now. I have to read the resonates, but you. Oh, nice. Foot of snow. Oh my god, that's crazy. All right, I'm gonna cut the YouTube stream off here. So if you're here on YouTube, thanks for being here.